In this question, we have two charged objects, and we're looking for the electrostatic force between the objects. Now, electrostatic force, just like any other force, is a vector quantity. It has magnitude and direction. So the direction is fairly easy. We look at it and we have two that are equally charged, that is, both positive or both negative. Let's assume they're both positive here. It says 1.0 Coulomb. We'll assume that's the positive. And therefore, they will repel each other. Two positively charged objects will repel each other. So as far as direction, they're going to be away from each other. That's easy, okay? On to the magnitude part. Now that's where we pull out our new Coulomb's law. So quickly, let's just draw our situation here. Two charged particles. They're 1 meter apart. They each have 1 Coulomb of charge, and therefore the force equal and opposite, repelling each other. Okay, so on to the magnitude, and we have that force being our K, our constant again, Q1, the charge of the first object, Q2, the charge of the second, and then the distance between them squared. And so plugging in some numbers, we know that our new K is 9 times 10 to the 9, and our units for that are newtons meters squared per Coulomb squared. And you can just get that off your formula sheet. And then we have the charge 1, which is 1 Coulomb, and charge 2, 1 Coulomb, and we divide that by our r squared, which in this case is 1 meter, all squared. Okay, now we were given really nice numbers here, and we can kind of continue to look at the concept more than the math, because multiplying by 1 and dividing by 1, that doesn't really have any impact. And if we check our units, always a good idea, Coulomb squared here and 1 Coulomb there and 1 Coulomb there cancels out the Coulombs. Meter squared on top, and we will be squaring that meter on the bottom, so we cancel out, and we are left with newtons, which is what we want and expect. And like I say, the ones don't do anything, so we're left with, and for sig fig's point of view, let's mark that as 9.010 to the 9 newtons. Okay, so if you're thinking, well, that's an awful lot of newtons, you're totally right. That's a crazy amount of newtons, 9 billion newtons. And just to give you a bit of a feel for that, that's about 200 times the maximum thrust of a full-size rocket off the launch pad. A crazy amount of force. So what does that tell us here? Well, using ones everywhere makes for an unrealistic question. True enough. Number 2, 1 Coulomb is an awful lot of charge. And so you're going to find that the rest of our problems, more realistic kind of numbers, we're going to be dealing a lot more with microcoulombs. And so that's a typical unit for these types of problems. And the third thing maybe you can take from this is that the electrostatic force is way bigger than the gravitational force. If you talk about, the charge in coulombs being plugged in versus the mass in kilograms being plugged in. So electrostatic force is very significant, very strong. And so dealing with it, we're going to go ahead and look at it in more typical problems, micro coulombs, and therefore come up with a little more realistic numbers.